Hi, welcome to Chemistry with Mrs. Miller. We're looking at Chapter 11, Gases, today. Now we have a couple of objectives we need to get done. And the first one is model the effects of changing the number of particles, mass, temperature, pressure, and volume on a gas using kinetic theory. Sounds a little complicated? Totally not. And we're going to review that kinetic theory from Chapter 10. Now we also want to be able to measure atmospheric pressure. If you don't know what that is, don't worry, we're going to go over it. And we're going to be able to demonstrate the ability to use the factor label method to convert pressure units. Don't let that scare you. Really simple, really easy. Just remember to take your time when you're doing this. So let's get started. Now, I said let's get started, but I meant let's get started slowly. The first thing we're going to do is look at our resource cabinet. Now, like my pictures or not, this is our resource cabinet. And our first one up here is our book about gases. So let's do a little review. So we know gases are one of the four states of matter. We know that these particles in a gas are so far apart they really don't have an attraction for each other. We also know that they have no definite volume or definite shape. They simply fill the container that they're in, no matter how big or how small that container is, be it a little vial or the atmosphere. Now, these particles, even though they're far apart, they still exert some pressure on their container. They're also very excitable. We can excite them by exerting more pressure, increasing the amount of particles, or increasing the temperature. So now that we've talked about exciting these particles, let's go look what that means. So the bottom one is that kinetic theory of matter. Well, let's go look at that. And how does that have to do with exciting those particles? So the kinetic theory of matter states that any submicroscopic particles are in constant random motion. And this produces kinetic energy. What is kinetic energy? Energy in motion. This is our random movement of our particles in our gas. Okay? So when gas particles collide, they undergo what we call an elastic collision. They don't gain or lose any energy. They simply change their line of movement. So they continue in a straight line, just maybe in a different direction. Now, the kinetic theory holds true for gases, except at very low temperatures or very low pressures. That's why we are going to deal with ideal gases. So we've done our review. So let's move on. We've looked at the skills that we have, so now it's time to add some more skills. So, pressure. Pressure is simply a force exerted on something, but by what or how? Well, we want to focus just on gas pressure, causing and affected by gas. Now, if gases are mostly space, how do we inflate something, say a balloon? Well, it's the pressure. Now, the kinetic movement of the gas particles within a balloon create a force which is greater than the surrounding atmospheric pressure. Yeah, you had that question, what atmospheric pressure was? Well, we'll get to it. Don't worry about it right now. Let's take a look at this balloon a little bit more. So, in my nice little drawing of a balloon here, you're going to notice that there's some gas particles. And these gas particles are bouncing off the inside of their container, in this case, the balloon. So, if we increase the amount of particles in there, we're going to increase this number of collisions. So, in other words, pressure is directly proportional to the number of gas particles. As we increase the number of gas particles, pressure is going to increase. If we decrease number of gas particles, we're going to decrease pressure. That's what that funny little A thing means. It means proportional. But we have to remember that when this is proportional, only when temperature and volume is constant. So how are temperature and pressure related? Let's go and take a look. Well, before we can get totally into this, we need to remember what temperature is. Now, if you've had me for any length of time, you're going to know that I've drilled this in since 7th grade. Temperature is really the measure of average kinetic energy. Well, we know any temperature of a gas shows basically how fast the gas particles are moving. So if we increase the temperature, in essence, we're really increasing the motion energy of the particles. Well, if the particles are moving faster, we increase the amount of collisions they're going to have with that wall. So if we increase that number of collisions, we're going to increase that pressure. So Again, pressure and temperature are proportional at a constant volume. So now let's take a look at volume. So gases completely fill the volume of their container, no matter what, right? So a reasonable conclusion for the relationship between gas volume and the size of their container would be, whoopsie daisy, that pressure is directly in proportional to volume. Let's take a look. Let's just let that sink in. Pressure goes down as volume goes up, and pressure goes up as volume goes down. Well, what does that mean? What can we look at? What's a real-life example? Well, let's think about trying to squeeze our balloon. We halfway inflate a balloon, and we squeeze or make that area that the air is allowed to be in smaller. It gets bigger, right? There's a lot of pressure on there. It makes it actually easier to pop. So let's look at this a different way. So let's look at my big container right here. So I have that big container. And let's just say that I, for sake of argument, have 10 particles of gas in there. 5, 6, 7, 8, 9, and 10. So they have a huge amount of surface volume, these 10 little particles, to bounce off of. So the chances of them actually hitting the sides of the container, a little bit less. But what if I went down to this teeny tiny little container and I put those same little 10 molecules in there, or particles? So now I got the 4, 5, 6, 7, 8, 9, 10. So I've put those same 10, they're not any bigger, they're not any smaller, they're the same size. And I've put them in this little container, and now they don't have as much surface area to bounce off of. So they're going to bounce off a bit more. So that increases the pressure. So now we've learned all about the things that affect the pressure. How do we measure it? So atmospheric pressure was a hard thing for early scientists to figure out. How do you measure that, really? Well, Evangelista Torlacidi, actually who is a male, developed a barometer. And basically the barometer measures the pressure exerted by the atmosphere. And he made this so accurately, it's this one over here, by the way, that if he went upstairs or went up or down a flight of stairs, that reading would change. So he used mercury. If you can tell, it's like an inverted tube filled with mercury. It would go up or down, depending on the pressure. Now, what he determined is that one standard atmosphere, or ATM, is basically 760 millimeters of mercury. Well, why wouldn't we just use millimeters of mercury? That's a lot of numbers when you start to figure that, one ATM is at sea level. And as you go up, that just becomes a little bulky. So 1 ATM equals 760 millimeters of mercury. Not a big deal. Same thing, just different language. So barometers only measure atmospheric pressure, but we need to know more than just atmospheric pressure. So we use something called a gauge. Now, gauges actually measure pressure above atmospheric pressure. So you have to remember, when you read a gauge, you actually have to, if you want to know the atmospheric pressure or the pressure plus that, you have to add them together or subtract them. Just remember that gauges actually measure pressure above atmospheric pressure. You're going to see this in your homework. So, we read barometers and millimeters of mercury, atmospheric pressure in ATMs, and gauges, they're in PSI, pounds per square inch. But in science, we have to use SI units. And the SI unit for pressure is a kilopascal, kPa. So how do we convert between all of them? Well, they all mean the same thing, they just have different numbers. So 1 ATM equals 760 millimeters of mercury equals 14.7 psi equals 101.3 kPa. Stop. Don't get confused. Take a deep breath. They all mean the same thing. 1 ATM, 101.3 kPa. 760, 101.3 kPa. 14.7 psi, 1 ATM. We're going to use a factor label method to change these. It's a really simple deal, but you have to write everything out. I don't want you to get scared here. I just want you to take the time. It's not a real hard deal. Just take the time. So we want to convert 35 psi to kPa or pKa. The way we do this is we write 35 psi. Not hard, right? Well, we're going to put it over 1. Don't ask me why we put it over 1. It's a math deal. So, let me fix this all here. We're going to take the 35 kPa, psi, and we are going to put it over 1, because it doesn't change the value of it at all. Now, does it? It does not. So, we have the 35 psi all over 1. And we have to convert it. So when we convert it, we're going to multiply it. Now I'm putting this in red so you know the difference. But what do we multiply it by? How do we know what to multiply it by? Well, we're starting at PSIs and we want to go to pKa. If we go back a page, we're going to find that out. So 101.3 kPa equals 14.7 psi. Just put that in your brain for a second. So we need to actually get rid of the psi. So what we're going to do is it's going to be 14.7 psi. We know that we need that, right? Well, it's actually going to be on the bottom. And above it, we're actually going to put the kPa, because that's where we're going. So we're going to 101.3 kPa. Please remember the P is the uppercase, the others are lowercase. So that's actually the end of our little equation. So now we just have to multiply out. But before we actually do that, we're going to get rid of our factors. So what's a factor? Our factors are PSI. Our factor label method, our labels are the PSI and the kPa. So when we do this, what we're actually going to do is we're going to draw this line. And we're going to cross out PSI, and we're going to point to where the other PSI is. Right there. And now we're going to cross this PSI out. And we're going to point to the other one. And so, because one's on the top and one's on the bottom, they cancel each other out. It's a math concept. So all we're left with, actually, when we're done, is 35 times 101.3. Now it's kPa. All over 14.7. Now we aren't going to label the PSI because we've already crossed them out. So actually, if you do this math, what you're going to find out is that it comes out to be 241.1904762 PSI. Or, I'm sorry, kPa. Well, we can't leave it like that. The reason we can't leave it like that, and you would get it wrong on a test, is because it's not in significant digits. If you look at this on our outside here, we have 14.7, which has 3 significant digits. 101.3 has 4 significant digits, and 35 has 2 significant digits. So we can only use 2 significant digits, which leaves us with 240, no decimal point, pKa. That's it. That's the factor label method. Not real hard. You're going to be using it a lot, so make sure that you take the time to write it all out and do it properly. So this is the end of section 11.1. This is the end of the lesson for tonight. Make sure that you go back and take your notes if you need to, and be prepared to work on homework in the morning. So have a good night. Thanks.